It's usually necessary to do some number crunching in order to make sense of data collected as part of a research study. Statistics is a field of mathematics involved with collecting, analyzing, presenting, and interpreting data. In this tricky topic, you'll become familiar with some commonly used statistical measures. Math tends to be a polarizing topic. You either love it or hate it, kind of like olives or black licorice. But it's necessary to embrace your inner mathematician if you want to understand how research findings are represented statistically. To do that, let's look at an example of some data that you might be interested in, performance on a class quiz. Let's say we have 19 students in our class who have just finished a quiz, graded out of 10. Looking at this list of numbers isn't the most efficient way to figure out how these students did overall. We can see with just a quick scan that Michoud and Redden got the highest marks and Stamp got the lowest. If the class was much bigger than this, it would be really difficult and time-consuming to scan through the data by eye. One way to get a better sense of quiz performance is to arrange the grades from lowest to highest, rather than alphabetically. This gives us an even clearer picture of how the class did. For instance, we can see that quite a few students got 7 out of 10. Something else you can do is to display the data in a graph by plotting a frequency distribution. Basically, you put your measure of interest on the x-axis along the bottom, in this case it's quiz scores, and the number of people who got each score on the y-axis on the left. Again, it's obvious that most people got a 7, but we can see the overall pattern of grades more easily in this figure compared to the table. A frequency distribution is a great way to eyeball your data, but it's not the only way. Researchers use a number of descriptive statistics to communicate findings in a dataset. Measures of central tendency produce a single value that is typical of the whole dataset. These are handy because they relay information about the data without having to scan the whole collection. The most commonly reported measure of central tendency is the mean, which is the mathematical average represented by the symbol x bar. To calculate the mean, you add up or sum, shown by the symbol here, all of your values, which we have affectionately referred to as x. Then we divide this sum by the number of observations we have in total, which in stat speak is referred to as n. The median is another measure of central tendency, and that's the midpoint value in your dataset. The mode is the most frequently occurring value. Let's look at these measures of central tendency in our quiz scores. By adding up all the numbers and dividing by our n, the number of quizzes, our mean works out to 6.4. Note that not one of the students actually scored a 6.4, since this wasn't a possible value, but it does give us a sense of how the group did as a whole. The median is 7, because if you arrange the values from smallest to largest, 7 is in the middle. There are 9 values less than 7 and 9 values more than 7. The mode is also 7, because it's the most frequently occurring score. 5 students got a 7. This gives us a very similar idea to what we already saw in the frequency distribution earlier, which told us that the scores on this quiz centered around 7. Other commonly used statistics are measures of variability, or spread of scores in a dataset. The simplest measure of variability is the range, which is the span between the highest and lowest values. For our quiz, the highest score was 9 and the lowest score was 3, so the range is 6. The degree of spread in quiz performance can also be calculated in a similar way to how we calculated the mean. One common measure is variance, represented as s squared, a number that indicates how much the individual scores deviate from the mean, and is calculated using squares. Let me explain. Keep in mind that the mean for this quiz is 6.4 out of a possible max of 10. We can simply work out how much each value differs from the mean, so 3 minus 6.4 is negative 3.4, and 4 minus 6.4 is negative 2.4, and so on. Note that these smaller data points give us negative values. After you finish calculating each value's deviation from the mean, if you add all of these together, you run into a problem. The positives and negatives cancel each other out, so you end up with a grand total that's something close to 0. Well, that doesn't appear to tell us very much about the spread of the data, because it makes it seem like there's no variability at all, and clearly there is. We saw what the data looked like, and we also calculated a range of 6. There's a simple mathematical solution to this problem. What we can do is square the individual deviations, like shown here, because a negative times a negative equals a positive. So that gives us a way to add all of these up. As long as we do the same thing to all of the values, this doesn't break any math rules. We add up these numbers to get our total squared deviation. Here's the variance equation. It's the sum of each observation, so each quiz, minus the mean squared, to avoid the numbers cancelling each other out, divided by n minus 1. Once we plug in our total deviation into our equation and divide by n minus 1, we get a mean squared deviation, or variance, of roughly 2.8. Values larger than this would indicate more spread in the values, and values less than this would tell us that the scores are more closely clustered together. If you're wondering why it's n minus 1, which is different than n that we used for the average, don't worry about that right now for our purposes. Some clever statistician calculated that n minus 1 is more accurate to predict variability than just dividing by n. Now what you'll see reported more often is the standard deviation. This takes the square root of the variance, and the number we get is roughly 1.7. This is in the same form as the scores that we used to get the mean in the first place. Keep in mind that you don't have to bother with squares or square roots to calculate the mean, because the mean doesn't give us a mix of positive and negative values. The standard deviation is used a lot for other types of statistical calculations, so it's useful to know where it comes from. Now, if you're a math head, then you probably find this somewhat interesting. But if you're math phobic, then you might be wondering when the heck you'll ever need to know this. Well, one area of research in psychology where standard deviation plays a big part is intelligence testing. Wechsler's IQ test is the most widely used measure of intelligence and is calculated so that if we plot a frequency distribution of scores in a population, the mean, or average, is 100, with a reliable spread of scores shown by the green shaded regions. These numbers here show the standard deviations above and below the mean. About 34% of the population is within one standard deviation above the mean of 100, and 34% is within one standard deviation below the mean. This means that 68% of the population is plus or minus one standard deviation of the mean, which works out to a span of IQ scores from 85 to 115. 95% of the population is within two standard deviations above or below the mean, so between 70 and 130, while pretty well everyone, or 99.7%, falls within three standard deviations, so between 55 at the low end and 145 at the high end. So one sensible conclusion that we can draw from this is that if someone's score places them at one of the extremes, say 160, we can be confident that, in terms of IQ, they're rare. Of course, this does not tell us that IQ is a valid measure of intelligence. That's a whole other debate. But what it does tell us is that IQ, as measured by modern intelligence testing, is fairly reliable. So far, we've focused on descriptive statistic, or displays of data. We can also use data to make inferences or conclusions, which is called inferential statistics. Inferential statistics allow us to make inferences or predictions about a population based upon observations of a sample. The fact that inferential statistics enable predictions makes them very powerful. But these aren't crystal ball predictions. Inferences are instead based upon mathematical calculations, which we won't get into in great detail, but it's worth reviewing some of the important concepts. Basically, the idea underlying this is that we usually can't test absolutely everyone we're interested in. Say we're interested in human beings in general. Then we could try and test all the humans on planet Earth and the handful of people working on the International Space Station. That would give us everyone, and we could be sure our data represent humans as a whole. But for a bunch of obvious reasons, this just isn't possible. There are too darn many of us, and we're all pretty busy. So what researchers do instead is to take a sample of the population to test, and then make inferences or predictions about the population as a whole. The term that's used most often to describe inferential statistical findings is statistical significance, a conclusion based on statistics that allows researchers to determine whether they can reject the null hypothesis. The null hypothesis is usually a statement that there's no difference, and is usually opposite of what the researcher hopes to find. Statistical significance is usually expressed as a p-value, and the conventional cutoff for a p-value is less than 0.05 or 5%. Let's look at an example to show how inferential statistics are used in psychology. This study, done at the University of Manitoba, tested the effect of an experimental manipulation on grades in a first-year introductory psychology course. The intervention was to get students to rethink how they explained failure by shifting explanations from things that are difficult to change, I did badly on that quiz because I'm dumb, to those that are possible to change. I did badly because I didn't study for that one. I'll do better next time. Half of the students were assigned to a business-as-usual condition with no rethinking training, and the other half had 2 brief training sessions where they learned healthy ways to think about poor performance. The students were not treated differently in any other way. Now, although the researchers were hoping to see an improvement in course performance with this rethinking training, the statistical null hypothesis is the default position that there's no difference between these 2 groups. The dependent variable they used in this study to look at the effect was the percentage of students who failed the course. What they found was striking. Far fewer students in the rethinking group failed the course. The researchers backed this up with a p-value of less than 0.05, which is usually indicated in graphs with an asterisk. This means that they found support to reject the null hypothesis that there's no difference between the groups, and so the authors can say with some confidence that their experimental manipulation did appear to improve overall course performance. If we accept that they designed their experiment well, which in my opinion they did, and their sample of intro psych students is representative of all intro psych students, we can generalize these findings more widely to this population. The take-home message: if you're faced with a setback in this course or any other, try and think of some adaptive ways to think about poor performance. Research using statistics shows that it does seem to help. So in a nutshell, this is a very basic introduction to some statistical measures used in research.